Hello, everybody, and welcome. My name is Anton Stroganov, and today I'll be guiding you through this webinar on linear components and applications of silicon nitride and LIGENTEC platform in particular. And I would propose to proceed in a way that we go through the content first, and then if there is enough time, we'll have short Q&A session. So please feel free to write me your questions even during the course of the presentation. So we have a list of them by the end, or probably I will be able even to address them during the course of the presentation itself. I also would like to mention that this session will be recorded and made available afterwards on YouTube and other platforms. To start with, a couple of words on LIGENTEC in general and our position and in the photonic ecosystem. We are based in the beautiful city of Lausanne in Switzerland, close to Geneva Lake and mountains. And here on this slide, you can see our offices, clean room facilities, and laboratories that we use. Looking into general supply and value chain structure, we are a chip manufacturing provider, and our platform is based on silicon nitride. We're able to cover all the stages from early prototypes to volume production, and we supply our customers with photonic chips, which later on can go into product modules or a system. We are part of the ecosystem, which means that we work and collaborate closely with software and design houses, as well as with the packaging partners to ensure smooth process throughout the whole product development cycle for our customers. We are happy to say that we serve our customers in a variety of areas, including such a hot topics as quantum applications or LiDAR systems. Besides, we address also more traditional areas such as telecom, datacom, metrology, and fencing. And you can learn more about what we can do for each of them on our website, web pages, and in other webinars given by my colleagues. Now, briefly about the content. This webinar is meant for all levels in general. From beginners to intermediary levels, they can learn something new, while experts can see how LIGENTEC platform can be a beneficial solution for different known components and applications. I will try to cover basic principles and things that you can do with those components, but will not go deep into details about the physics. So for those who are interested in the more in-depth look on how each of the devices work, I will provide some of the useful and great links for sources of information on each of the topics. So to start with and to make a basis for the following parts of the presentations, several things on LIGENTEC platform. What we do, we call our approach a modular, as it consists of several parts. We start with a basic process, simple single layer waveguides with specified silicon nitride thickness. And what distinguishes LIGENTEC from others here, and it's important for all the next discussions, is the capability to deposit thick films and to process them, as I indicated here. Okay, so we start with a basic process, and we have simple waveguides, but we would like to enhance the functionality. And for that, we have additional modules. You can make, for example, a waveguide, or do a local cladding removal, or integrate heaters on top of your devices for thermo-optical tuning. And the main advantage of our platform is cross-compatibility of all these modules, which means that you can combine all of them on the same chip, having any kind of structure and functionalities that you may need. As you can see here, on the same chip, you can see all the possible combinations of these modules. We provide access to our technology as a part of R&D projects, dedicated wafers, or also through the MPW multi-project wafer runs for fast prototyping. And the lead times can be as short as 2 months here. Well, as I mentioned, we work with silicon nitride. Why? Why not to be stick to traditional silicon photonics? Silicon nitride is a flavor of silicon photonics, and therefore it holds the same benefits, while also having some additional advantageous features, such as, for example, wide transparency from visible range to near and mid infrared. It can handle high power because there is no two-photon absorption. It has intrinsically higher thermal stability and lower loss. But as I mentioned, we work with thick silicon nitride, and I especially focused on this fact. So what kind of benefits can you extract from here? Well, the mode is very well confined inside the waveguide, as you can see from here. And therefore, even lower losses than for any other silicon nitride platform can be achieved, because the mode is confined and it doesn't see so much roughness of the side walls or of the top and bottom parts. By low loss here, I mean that losses of below 0.1 dB per centimeter can be achieved for near infrared for telecom wavelengths. Moreover, you can achieve very small footprint devices, or you can have very tight bands because, again, your mode is confined. It's very similar to silicon photonics and is in great contrast to, let's say, other platforms of passive devices such as glass photonics or low confinement platforms, even of silicon nitride. Due to high confinement, you feel also less fabrication-induced phase error in your devices, which is very important for my applications of the devices, as I will explain later on. Now, let's start with one of the most important things, probably, about photonic integrated circuits: how to get light on a chip and from a chip, and how to do it efficiently. And I believe that everybody who have ever worked with photonic integrated circuits have faced this challenge, but I will briefly introduce it again. So to connect your chip with external world, which means with an external laser source, for example, or with a detector, you need to interface them with fibers in the majority of cases. Fibers are not the only solution. Lenses, for example, or objectives or any kind of microassembly can be used here as well, but similar problems and principle applies, so we will be stick to example of a fiber here. Let's take a look on the top left part of the slide. Here you can see a standard telecom single mode fiber and a waveguide. Obviously, there is a mismatch of a size. And as one can remember, efficiency of coupling is generally defined by an overlap between the modes in terms of dimensions and in terms of alignment. And here you can see a mode of a fiber in our case and the mode of a waveguide. Again, there is a mismatch. Efficiency is the highest when they coincide in dimensions and when they are perfectly aligned, and lower in all the other cases. As you can imagine, there could be two approaches foreseen to solve this problem of a mismatch and inefficient coupling. And the first one is to decrease the mode field diameter of a fiber. The second one will be to increase the mode field diameter on a chip. Talking about the first option, about decreasing fiber mode field diameter, there are some special fibers available on the market and widely used for experiments in photonic community. These are lensed fibers and ultra-high NA fibers, which can provide you with a mode field diameter of 2.5 to 4 microns in diameter, approximately in telecom wavelength range. Well, it's a great effort and help. It works very well in a lab condition, though there are some drawbacks. And they are mainly induced as these fibers are kind of specialty fibers. First, its cost, then its fabrication tolerance, and the third part, that you have a limited supply. And here I mean that it can be sometimes challenging to find a fiber which meets all the requirements that you need for your system in terms of wavelengths of operation, about being broadband, about being polarization maintaining, and so on. Okay, so we can take a look on the second approach that we discussed previously. We can play with the mode field diameter on a chip side. Let's start with a standard waveguide. You can see here how the mode is distributed here. And we would like to increase the mode size as we discussed. The first thought, an obvious thought, would be that we can increase the waveguide dimensions, like here. Okay, we can see that it works well, but the mode is rather asymmetric. And it can work very well for example, chip-to-chip or laser diode coupling, but probably will not work well with fibers. Or otherwise, we can try to do it another way around. We decrease the waveguide cross-section, and in this case, the mode is pushed out of the core of a waveguide, effectively enlarging its size. In this case, you can see that it's much more symmetric or even larger than in the previous case. And from here, we can see that having an opportunity to tune waveguides cross sections by both width and thickness, it's important to be able to get tailored mode profiles and to be able to achieve high coupling efficiencies for different fibers, lenses, and for chip-to-chip coupling. Typically, for such kind of tapered devices, as we call them, for silicon photonics and silicon nitride photonics, mode field diameters of approximately 2 to 3 microns can be achieved. And the question rises, does it mean that we now solve the problem, taking into account that we have all these specialty fibers which allow you pretty much the same mode field diameter? The question is no, and here it's why. So even if theoretically we can achieve very good coupling efficiency, we still need to assess how it will work in the real world conditions. And probably one of the most appropriate things to check here is alignment tolerance, or basically how your efficiency will change with non-perfect alignment between a fiber and a waveguide. Let's assume that we have a spot size converter on a chip, which makes the mode size very similar to the one of a lensed fiber, let's say, for the start. Then we start moving the fiber and checking additional loss induced. And here you can see what we have in terms of power distribution in this case. Doing so, we can learn what misalignment is needed to achieve 1 or 3 dB level. And you can see that if we misalign fiber and a chip by just 1 micron, we will have more than 1 dB loss already. And with 1.5 microns of misalignment, it already reaches -3 dB, which is really a lot, and in the majority of cases can be a killing factor. So if you plan to package, for example, your chip as a part of a system or as a part of a subsystem, let's say, some problems may arise here, as for example, misalignments induced due to glue shrinkage, or if you work with fiber arrays, as an example I provided here. So basically, during the fabrication of fiber arrays, you can have slight imperfections of fabrications, which mean that your fibers will be slightly displaced from perfect positions. And this will cause the loss in the final package device. So though it can be still applicable for lab experiments and for prototyping, and I would say that this solution, namely standard silicon nitride or silicon tapers, is still widely used by a community. As a next step, let's assume that somehow we managed to make a spot size converter on a chip to increase our mod size to 10 microns. And basically, we do the same alignment tolerance check with SMF fiber. And here we see that 1 dB level tolerance now is at approximately 2 microns level, which looks much better. And that's the main reason why recently we put quite a lot of effort to develop such a spot size converter for our platform. And I need to say that we managed to achieve it. It works efficiently with standard SMF fibers. It's broadband in contrast to grating couplers, which are usually considered to be an alternative solution for SMF fibers coupling. And also it works for both polarizations, which is also a great contrast to grating couplers. What is also great, it's an integral part of a chip, and therefore it's tolerant and scalable solution, which now we can offer as a part of our offering to our customers. Okay, great. So now we discussed how to deal with the fibers. So in some cases, in some systems or applications, coupling is done not only with them, but sometimes uses also free space inputs and outputs for different applications. And here, as an example of application, could be an optical phased arrays. The concept and principle is well illustrated here on the right. We have a system which splits a beam into several paths and emits them afterwards. And each path also contains a phase shifting device. And by changing the relative phase shift between different emitters, one can achieve control over the direction of propagation of the output beam. Also, probably what we can mention here is that the phase difference in such kind of devices can be achieved not only by a phase shifter per se, but also by changing, for example, a wavelength of aberration. And I believe this node can be useful for us, and moreover, it will be referred later on today. So optical phased array, they are being investigated a lot at the moment, as they can serve as a basis for solid state LiDAR systems without any movable parts, or otherwise they can be used as a part of free space optical communication links, for example. And on a chip, an optical phased array system will look similar to this one on the left. So you have your input signal, which is then split into several paths. Phase shifters on a chip can be implemented by thermo or electro-optical effects. And as emitters, people typically use grating couplers, and they can be used to achieve vertical output from a chip or to allow arrangement of a whole 2D array of emitters, as you can see here. Or another approach here could be just to use simple waveguides on a facet of a chip. As you may understand, there are several important things for such kind of systems. And going step by step, they are: first, you should have a good control over your emitters. And our platform allows both types of interfaces, namely grating couplers and edge couplers. And moreover, we can do very dense integration and arrangement them on a chip, which can provide you a better degree of control over your output beam. Moreover, for edge couplers, having a flexibility in choosing the film thickness and widths, you can have a great control of the numerical aperture of the output beams. Then we go to the part of the propagation. And here, what is important is phase stability of the passive part itself, as well as a capability to have this phase shifters on a chip, which can be implemented, for example, by integrated heaters. And of course, the last part that we can see here is splitters. There are many of them typically involved in such kind of system, and therefore they should perform very stable and be in low loss. The question here is how to achieve efficient and low loss splitting on a chip. And this question is important not only for optical phased array systems, but pretty much for every circuit you can imagine, even for simple MZIs. And here there are two main approaches to split the light on a chip, which are commonly used. And typically it's hard to say which one is better, and it depends really a lot on a particular case and application. So I will try to briefly address both of them. First approach is a directional coupler, as you can see here on the left. They consist typically of two waveguides alongside each other. You can see a cross-section monitoring here. And while propagating, the light is transferred from one waveguide to another and back, as you can see here on this monitor, which covers the whole propagation length here of the device. And in the end, the length of the device is chosen to fulfill the necessary splitting ratio that you target for your application. The device principle and approach to its design is very well described in the numerical example, which you can find on their website or following this link. But what is important for us application-wise is the pros and cons of these kind of devices. And the real advantages of directional couplers is that they are super easy to design and that they can be very low loss. But the drawback here is that they have a high fabrication sensitivity, and also typically they have quite large wavelength dependence of the performance. An alternative approach to splitting the light on a chip could be MMI couplers. So it's the part on the right, and its device is based on multimode interference. If you'd like to learn more about the underlying physics and principles, you can take a look on this paper because it describes it very well. But I will just give a brief basis and essentials. So there is one or several single mode inputs which come to a section of a multimode waveguide, which is much wider. In this section, you have several modes which are excited and propagating in the device. They interact with each other. They form an interference pattern and number of so-called self-images, as you can see, for example, here. And the whole trick is to choose the device length in a way that you can have a required number of self-images or required power splitting ratio. And when you split it here in this plane, your multimode section ends, and you put back again your single mode channels to collect and to guide your corresponding fractions of power. The pros of the MMI couplers are that they are typically very broadband and very compact. And comparing them with directional couplers, they are much more fabrication tolerant and can have much more flexible configurations, which I will describe a bit more in details later on. Probably the only drawback that people usually see here is that they are more complicated to design, and you need to spend really more time and effort trying to get the device which fulfill perfectly your target application. And what I would like to mention here is that LIGENTEC PDK, developed together with VLC Photonics, has a variety of MMI couplers included in it, and they are basically ready to use devices. As an example here, you can see 72 by 28 MMI splitters. I'm talking about flexibility of splitting, which has very precise splitting ratio over a wide range of wavelengths. And yeah, and all of the components that we have in our PDK, they are verified, which means that we fabricated and measured them many times to confirm that they work stable and its fabrication is reproducible. Again, just speaking about possibility or opportunity to implement MMI in a platform, I believe it's not enough. That's why I decided to put a bit of a measurement data. Again, these MMIs belong to LIGENTEC PDK, which we developed jointly with VLC Photonics. And here you can see examples of 1x2, 2x2 MMIs, and some customized splitting ratio 2x2 MMIs for both polarizations. and measure it in a quite broad range of wavelengths. And you can see that they are really broadband, that they perform well for both polarizations for T and TM for the same device. They are very reproducible and they are low loss. Now to the one of the most commonly exploited components probably in integrated photonics, which can be used for both linear and nonlinear applications. It's ring resonators. There are two main configurations which serve as building blocks for any kind of ring-based devices. The option A, where a ring is coupled to one bus waveguide. This configuration is typically referred also as an all-pass configuration. And option B, when there are two waveguides coupled to the same ring, and this option is typically referred as a drop configuration of ring resonator. If you would like to learn more about underlying principles of the devices, you can take a look on this publication, and it really describes very well all the physics happening besides all these coupling regions and cavities. But what I would like to mention today is just several important things from engineering point of view and the things which are needed for basic understanding on how the devices are working. I believe there is no need to explain how resonator works and what is resonator in general. Here, basically, if you will take the simplest configuration, the light is transferred from a waveguide to a ring resonator, which is a cavity. And if a wavelength of operation can fit inside the ring integer number of times, it forms a resonant condition. To explain better what it means, let's assume that we have our input signal here, and we have our detector here. And we try to sweep a wavelength of operation. I will try to use these plots to explain how it works. So basically, if we are somewhere off the frequency of the resonance, we have just the whole amount of the power going to the detector. But when we approach a resonant condition, we have a peak in the transmission, which means that we achieve this resonant condition. Basically, there are two values that we need to mention for further understanding. The first one is a quality factor, or also it can be referred as a line width. They are really correlated parameters. And this characteristic measures how wide is a resonant peak. And therefore, it also characterizes losses in a cavity. The higher the loss, the broader the peak is. And also, we will operate with a extinction, which means, or which characterize how deep is your resonant peak. Now, let's take a simplest configuration, again, all-pass configuration. And there is an interesting degree of freedom or parameters that one may vary. It's the spacing between the ring and the waveguide. And this parameter influences the performance of the device. And here I mean both the quality factor and extinction. And keeping the things simple, its effect can be described probably as following. So let's assume that we found a spacing which gives us a good deep resonant peak with a transmission close to zero during the resonance. And we will call this configuration a critical coupling. Basically, that means that we managed to find a configuration satisfying a specific relationship between the amount of light coupled from a waveguide and to a waveguide from a ring, and also having a specific relationship to the losses inside the cavity. Then what we do, we make the spacing between the ring and the waveguide smaller, which means that more light is generally coupled from a waveguide to a ring. Here, what will happen with our transmission plot is basically that extinction will be smaller and Q factor will be also smaller, which means that your peak will be wider. Otherwise, if we do it other way around, so basically if we increase the spacing between the ring and the waveguide, we will achieve what is called undercoupled condition, when you have also smaller extinction, but your peak is more narrow, which means that you have higher Q factor. And as I mentioned, we call this undercoupled regime. So generally, these conditions are specified for chosen wavelengths and may differ if you go left or right from it. Or if we will talk about even more complicated cases, your polarization, your mode of interest, or your ring widths and other parameters also influence the regimes that you can achieve. There are different tricks and approaches to allow you to reach the exact device performance by dealing with shapes and configurations of the coupling regions or coupling waveguides. One of them is what is called pulley couplers, which can help you to achieve very good coupling conditions for very broadband range. And if you'd like to learn more, you can take a look on the cited publication here, because it describes the procedure of the design of such kind of couplers very well. And an obvious note, the higher Q factor is for a platform, the better, because it opens a way to more sensitive devices and to better filters. And LIGENTEC and SICK films can do a great job here. For ring resonators fabricated in our platform, Q factors of 2 millions and more are typically achieved, and up to 15 millions were shown. So being compared with silicon platforms, where the Q factor is typically of order of tens of thousands or probably hundreds of thousands, obviously the Q factor is much higher for SICK film silicon nitride. Also about applications. So I mentioned some filters, and it's where rings are mostly used if we're talking about linear applications. There are many configurations and functionalities known and investigated, such as, for example, the multiplexers based on rings. And here in this configuration, you have your rings in add drop configuration. You have, and they are coupled to the same waveguide, input waveguide. You have your signal coming inside this waveguide, which is carried by several frequencies. And then by adjusting the resonant frequencies of the rings, you can split them into several channels. Otherwise, there are other widely used configurations, such as Crow or Vernier filters, which employ a series of coupled rings to achieve desired stop or passband response for a filter, or higher extinction ratios, or sideband suppressions. And to make such kind of systems or filters tunable, or to accommodate for small fabrication imperfections that you may have in every platform, you can integrate heaters on top of it. And the idea here is simple. So you heat your material, you change its refractive index, and therefore you change the resonant frequency. And generally, this tuning can be quite significant, I would say. And in our platform with integrated heaters, we managed to show tunings of more than 500 gigahertz and shift of several PIs in MZI configurations. In the last part, I'll just briefly touch on array waveguide gratings, as it may be a separate webinar on its own, I believe. It's probably one of the most complicated photonic components to design, and it has quite a broad list of parameters to be optimized. In general, it looks like this, and I've taken an image from Wikipedia as it nicely illustrates the principle. This component is typically used for multiplexing and demultiplexing applications and for signal routing. So if we will try to simplify it, it takes a channel with multiple wavelengths, with a signal which is carried by multiple wavelengths, and then splits them into several channels according to the wavelengths. Or it can be also used vice versa. So if we will try to describe it a bit more in details, there is an input, one or several, which contain a signal, and it comes to a region of almost a free space propagation. Well, it's still a waveguiding structure, though it's very wide. And this region here and here, they're typically called or referred as a star couplers. So your signal coming here, going through this propagation region, and then it coupled to a number of single mode channels. As you may see from sketch here or from GDS of a real AWG here, there is a length difference in these channels. And basically, the wavelength dependent phase difference that is introduced causes a wavelength dependent tilt at the outgoing wavefront associated with the shift. And therefore, you can guide a particular color of light to a particular channel of interest. It's in principle very similar to the principle of operation of optical phased arrays, as I mentioned before. Again, as a device is purely passive and is based on the phase relations, it's very important to have a low fabrication-induced phased errors here. And also for the majority of real applications, it's very important to have low temperature dependence, basically to ensure that the device will work well and stable if ambient condition changes. In the middle part of the slides, you can see some measured responses of our AWGs. So here, different channels are represented by different colors, and you can see a clean, repetitive pattern. And generally, in AWGs, there are two main types of passband shapes. It can be either a Gaussian or a flat top. And here, for this particular example, you can see that the response has Gaussian shape. Who are not experts in AWGs, there are several important parameters to look at. And one of them is a crosstalk. Basically, it's the amount of light which goes from one channel to a neighboring channel. And here you can see basically it will be defined here at a level of -30 dB pretty much for this particular device. And another important parameter or thing to consider while taking a look on the characterized samples is insertion and propagation laws that you have for your device. And basically it's defined by a position of a peak here from 0 dB value to the peak position. I should mention that in these measurements, they also include the losses induced by the setup itself. So it's not only the loss induced by the device of AWG. And similarly to other components which can be implemented, it's thick silicon nitride platform. AWGs can work for both polarizations. So here you can see the measured response of the same device for TE polarization and for TM polarization. As a beautiful example, here on the right, you can also see an AWG that we fabricated for visible wavelength range. And you can clearly see how the light is split into several channels with several colors. Moreover, for those who are interested, there is a great paper from HP Enterprise that they presented on OFC. which is showing a great potential of wavelength division multiplexing applications on chip using our platform, as we can basically fulfill the need of low loss, of low phase error, and low temperature dependence, as I mentioned before. Again, some more data to share on real examples of fabricated samples. From the very start, we wanted to demonstrate a capability of thick film platform for fabrication of AWG devices. And again, here we had a great development together with our partners at photonics. Here on the left, you can see one of the very first AWG sample chips that we fabricated, and you can see several AWGs fabricated on a same chip, which is 5 by 5 millimeter in size. And since then, we fabricated quite a lot of different devices which cover different wavelengths of interest. So it's obviously telecom wavelengths, O and C bands, which work for different polarizations. It's visible, as I already shown. It's near infrared, and also in the papers that I referred previously from HP Enterprise, they demonstrated AWGs with operational wavelengths of around 1 micron. To summarize briefly what I have shown during the course of the presentation. So what is LIGENTEC and how it can be a beneficial solution for photonic integrated circuits and linear applications of them. So what we can provide is a mature and versatile modular silicon nitride platform with a basic process of tunable thickness of silicon nitride. And on top of it, you can introduce additional modules such as integrated heaters, local gradient removals, and others. There are a variety of them available, which I haven't covered during the course of these presentations, such as, for example, U-grooves, which can enhance your packaging capabilities, or arbitrary facet definition, which means that we can fabricate a chip with any form factor that you may need for your application, and many other interesting features. So we discussed briefly what is the benefits of thick silicon nitride platforms. As any silicon nitride platform, it has very wide transparency range. You can handle high optical powers with more than 10 watts of continuous waves. We demonstrated it with several collaborative works. You can achieve very low loss, below 0.1 dB per centimeter in near infrared. You can have low phase errors induced by fabrication in your phase sensitive devices. And also you can have very small footprint for your devices because the mode is very well confined inside a waveguide. Talking about available components and PDK, we have a set of broadband, low loss, and fab tolerant components, which are ready to use in our PDK. It's spot size converters for both lensed fibers and ultra high NA fibers, as well as for standard telecom SMF fibers. We can do very high Q ring resonators with 2 millions and more. We have a whole library of ready to use MMI components and AWGs, as well as our platform can allow you to do very low loss delay lines, which is obviously needed for a lot of different circuits and applications. Probably I haven't covered this part a lot during the course of today's presentation, but what I can mention is that you can put more than a meter of a waveguide on a small chip, which is less than 5 by 5 millimeters in size. Besides the linear part that we partially covered and discussed today, there are a lot of other interesting things and capabilities to mention. Of course, it's nonlinear applications where dispersion engineering comes in place, and a lot of interesting and exciting things were discussed and demonstrated. such as frequency comps, supercontinuum generation, and a whole bunch of parametric processes. And a thick film is a key here. So it's one of LIGENTEC main expertise. And also another hot topic, which is discussed and investigated a lot during the last days, is heterogeneous integration with co-integration and co-packaging of different material platforms such as silicon nitride, silicon 3,5 materials like lithium niobate, and so on. And recently we demonstrated several quite impressive results, which you can take a look at following these publications. Otherwise, there is a whole batch of interesting works and papers from our partners demonstrating different great capabilities and benefits of SiC silicon nitride platform in a variety of fields and in a variety of applications. If you'd like to learn more about what applications can be targeted and which publications came out recently using our technology, you can refer to the web page of the technology on our website. And with that, I'd like to finish my presentation. I would like to thank you all for attendance, time, and your attention.